Okay, we can start. Not all the guests are still online, but anyway, we waited 5 minutes, so we are going to start. I introduce myself. My name is Andrea Nicora. I am General Manager of Termomeccanica Service Division. We are very happy and proud of your participation in this event, and we thank you very much for that. The main reason for this presentation is to celebrate Termomeccanica participation in the project of the first combined cycle power plant with Class H gas turbine, for which Termomeccanica has supplied the main boiler feed pumps. And this project is a good flagship of Italian technology, and Termomeccanica took part to this. Boiler feed pumps are a very critical item, and they are, let's say, in terms of performance, thermal transients, operational transients, and the various operating conditions. In the next slides, we will give you some highlights of previous references by Termomeccanica, specifically for boiler feed pumps. Then I will leave the word to my colleagues. First will be Mr. Matteo Toselli, who is the head of engineering department. He will carry out an in-depth presentation of this new boiler feed pump. Then Mr. Fabio Torpia will explain how our test circuit has been realized, and then so he will introduce especially the hot temperature test circuit of our test center. Then we will leave the connection to our colleagues of the test center. Mr. Massimiliano Borghetti, head of research and development, will show you the pump under testing and all the data collection from the test field. Then we will come back in the meeting room for a question and answer session. Totally, it will take around 1 hour. Of course, at the end, let's say you can send all your questions during the test phase. So we will collect the questions and try to answer to all of them. So we can go to next slide, please. Okay, let's say Termomeccanica is a company with old tradition. It has been established more than 100 years ago, and since 25 years, it's a private company. We are specialized in engineered pumps and pumping systems. Our main sectors are not only power generation, we are active also in the oil and gas, in the desalination, in the water handling sectors. Now in the next slides, we will focus especially on the power generation. In our history, we have supplied pumps for different types and different technologies of power generation plants, from conventional steam to combined cycle to geothermal and to nuclear. Okay, mainly we supply the main pumps of this type of power plants, which are boiler feed pumps, condensate extraction pump, water cooling pumps, and intakes. The boiler feed pumps can be realized according to different types of API 610 configuration: BB2, BB3, BB4, and BB5. We have experience in all of them, and next slide we will show some references for each of this type. In the last 50 years of history, we have installed a total electrical capacity in terms of just boiler feed pumps of 2,500 megawatts, ranging from 150 kilowatts up to 30 megawatts. So a wide range of nominal power for the boiler feed pumps. And we have supplied more than 1,000 boiler feed pumps in more than 35 different countries worldwide. Okay, next. Okay, here are some examples. This one is a boiler feed pump with a power rating of 30 megawatts. installed in a power plant in southern Italy. It's a conventional steam power plant. This pump is running since more than 30 years, so it has performed very well during all these years. And this shows also that Termomeccanica is able to cover a wide range of power ratings, and specifically the pump that we are going to present today is in the medium range, not in the upper range. Next, please. Okay, this is another application. This pump, also the previous one and this one as well, are BB5, so it's a barrel type. This pump was supplied around 10 years ago for a power plant in Egypt. The peculiarity of this pump is that it was for a supercritical thermal cycle. In fact, you can see that the fluid temperature is very high. We are at 220 Celsius degrees. Next. This is a typical boiler feed pumps for a combined cycle power plant with a power rating of 2.1 megawatts. We have supplied 10 of these pumps for the project PP12 in Saudi Arabia. End user was Saudi Electricity Company. And for another project called the PP10, we supplied 120 identical pumps, even if smaller in size. Okay, we can go to the next one, please. This is an example of a BB3 pump. BB3 pump is actually a split casing pump. Is another solution we can provide. Let's say normally is most common the BB4 or BB5 configuration, but we want just to show that this is another possible solution for a boiler feed pump. This one was installed in the Middle East region, let's say 4 years ago. Okay, and this is another very specific application. This pump is a BB2 configuration, radially split. We have supplied for a nuclear power plant in India, Rajasthan. The end user is a Nuclear Power Corporation India Limited, NPCIL. Particularly on this pump, we did two very heavy-duty tests. One is called the dry running test, which is practically a test in which we close the suction valve on the pump, and the pump is running a few minutes without water. And specifically, we check the condition of the mechanical seal in the dry running, and they shall withstand this dry condition for a few minutes. The other test was a thermal shock test. We have, let's say, done positively this test, so our pump has been accepted and homologated by the NPCIL company. So let's say this is an example that we can provide pumps for different type of power plants with different configuration and with different technology. Okay, so our strength for sure are flexibility and capacity to adapt to customer needs, especially let's say for the engineered pumps. Now we will start introducing our project for the new generation of boiler feed pumps. The drivers of this new project have been efficiency, so maximum attention to the efficiency in the project and design of the pump, and reliability. So these have been the two main drivers for this new project. Now I will leave a word to my colleague Matteo Toselli, who will explain more in detail the technical characteristics of the boiler feed pumps. Thank you very much.
Okay, good morning to everyone. Thanks to Mr. Nicola for this presentation. Now I will give you some information related to the pump that we are going to test today. This is one of the various type of pumps that TMP can supply with for the boiler feed application. It has been developed in order to fulfill all the performances requested by the combined cycles plant using the new Class H gas turbine. This type of pump is an horizontal multi-stage between bearing, radially split, and single casing, so without external barrel. That means this name is BB4 according to API 610 nomenclature. TMP pump model is MES 210. It means that discharge nozzle is 8 inches and the number of stages are 10. The nominal design flow is 419 cubic meter per hour, while the head is 2,176 meters. The installed drive power of the motor is 6 megawatts 0.3, and we use an hydraulic coupling to change the speed from 1,800 RPM to 2,900 RPM. The maximum fluid temperature of this pump is 157 degrees Celsius, and the efficiency is 81%. This pump must work on 11 different operating points, and that means that it has been optimized as a compromise between all of them. However, in our portfolio, the family of the pumps of this family can reach very high efficiency, up to above 84%, depending on the size, on the speed, and of course on the fluid temperature as well. Okay, in this slide, we can see the section of the pump that we are going to test. You can see the 10 impairs and diffusers. They are manufactured using high quality investment casting process, and then they are polished in order to have a very low ruggedness and very high efficiency. The first impeller has been designed for low MPSH are requested, and it is different from the other stages that are designed for high efficiency. After the first impeller, there are 2 stages before the bleed-off casing, and then there are 7 stages after the bleed-off casing. The bleed-off connection is used to take a part of the flow, and with the pressure of the 3rd stage in order to feed the medium pressure circuit of the boiler. However, the pressure of the bleed-off can be changed simply changing the position of the bleed-off at a different stage, or changing the type and geometry of the impeller before the bleed-off. The mechanical seal is a single mechanical seal, and it has been designed up to 20 bar gauge of dynamic pressure, and it is flushed by plant 23 seal system, water cooled, and can be serviced without disassembling the pump, but only disassembling the bearing supports. Inside the bearing supports, we can find the thrust bearing, which is used to bear the residual axial thrust that is partially balanced by the balance drum installed on the rotor. The thrust bearing is a tilting pad type, directly lubricated for a very high rotor speed, and is a self-equalizing design for to have a very uniform load distribution on the pads in order to increase the maximum allowable load and also the reliability of the bearing itself. The journal bearing are sleeve type, 4 lobes, that means very high rotor stability. The impeller has a shin fit design on the shaft, which is forged, and this kind of design is very important in order to reach a very high level or dynamic balancing on the rotor. That means very low dynamic loads and vibrations. The rotor of the pump has been sized with a very big diameter and low bearing span in order to minimize the shaft deflection at startup. And the lateral analysis has been made in order to check and avoid any critical frequencies inside the full speed range that in this case is quite wide. For the same reason, we have made also the torsional analysis that has been performed not only on the pump shaft but also on the wall train. So it is composed by the rotor of the pump, the rotor of the hydraulic coupling, and the rotor of the electric motor connected together with the flexible couplings. The aim of this analysis is to avoid any dangerous torsional resonances. Regarding the casings of the pump, we have made a lot of finite element method analysis in order to verify all the operating condition of the pump and the maximum, the condition with the maximum pressure inside during the workshop hydraulic test. The maximum pressure for this pump is 442.5 bar gauge. We have also made a lot of analysis, method analysis, to verify the behavior of the pump during the sudden temperature increase or sudden temperature decrease in order to avoid any stresses on the tie bolts and any leakage on the casings. We have also made also made analysis on the pump and the base plate in order to analyze the behavior, the dynamic behavior of the skid on the full design speed. The geometry of the impeller, diffusers, and casings that have been used in this pump has been used also several times in other projects and plants, and has been developed in TMP using CFD and then tested with prototypes in our test center. The first stage impeller has been optimized, as I've already said, for low MPSH requested, but we have the possibility to install a double suction impeller with even higher suction capabilities. And the other stages are optimized for a very high efficiency. Okay, in this slide we can see the skid of the pump in the configuration we are going to test today. On the right, the top right of the slide, we can see the electric motor, which is water cooled, and it is a medium voltage motor. It's connected to the hydraulic coupling with flexible coupling. The hydraulic coupling is used to change the speed of the pump. It has an integrated lube oil system. You can see in orange color all the pipes of the lubrication circuit. The lubrication oil is used to lubricate the bearings of the pump and the bearings of the electric motors. And all the oil is cooled by two heat exchangers on the left of this slide. One is used to cool the lube oil of the bearings. The other one is used to cool the working oil of the variable speed hydraulic coupling. The pump is connected to the hydraulic coupling with a flexible coupling, and it is instrumented with temperature and vibration transmitters for the real-time machine monitoring system. All the components are installed on the base plate, which is fabricated, drain, ring, and pan, and it is designed for grouting for higher installation rigidity on site. Now, just a few words on the hydraulic coupling. The model is the Voigt 650 SVTL 30 HP, and the hydraulic couplings are machines that use Voigtner principle to transfer the torque and the speed from the motor shaft that has a constant speed to the driven shaft that can change the speed. In channel color, you can see the scoop tube that is used to change the level of the oil inside the hydraulic coupling. Increasing or decreasing the oil level inside the hydraulic coupling, we can increase or decrease the torque and the speed transferred to the second shaft. Another system that the TMP can supply in order to change the speed of the pump is the variable frequency drive. In this case, the VFD can change by means of its electronics the speed of the motor and the speed of the pump, changing the frequency of the supply tension to the electric motor. Both systems, however, have pros and cons, and their selection is often made according to the specific requirements of the customers. Anyway, TMP can supply both solutions as well. Okay, thanks to all of you. Now I have finished. Mr. Torpia will give you some information about the test we are going to start.
Good morning, everyone. Thanks to Matteo for introducing myself. My presentation will be a brief introduction to the scope of a high temperature test. Usually, pump performance tests are executed at ambient temperature, and the results are then corrected at the design temperature using mathematical formulas. TMP is anyway able to perform the performance test at higher temperature than the ambient, as we will demonstrate later on. And so in order to match the design temperature. The scope of high temperature test is to check the correct mechanical operation of a pump at the design temperature, and also to verify the conformity of the machine of the contractual requirements. During the test, some parameters, as shown in the slide, are measured. For example, pump, temperature, flow, power, and some are calculated as total head, efficiency, and NPSH. For example, on the right hand of the slide, there is the formula of a total head, where pressure and at the discharge and suction flange are inputs, and also dynamic differential head also added and calculated as total head. Now we, in the next slide, we pass to the high temperature test procedure. The test has a setup procedure of 4 points. First step is to pressurize the circuits in order to have the required NPSH to correctly operate the pump. When the circuit is pressurized, we can start up the boiler feed water pump in order to increase the fluid temperature by dissipating the mechanical energy. So the fluid temperature rise, and we can regulate it with the heat exchanger. When the temperature of the water is stable at 157 degrees in this case, or at the desired temperature, we can start the real performance test and check every operating point by regulating valves and rotational speeds. As we show in the next slide, we will check today the rated flow and rated head, bleed off flow and bleed off head at 2 different rotational speeds, that is 2000 RPM and 2800 RPM, which are velocity close to the boundaries limits of the operational of the hydraulic coupling. Before I hand it over to my colleagues of the test room, we briefly go in the detail of the test circuit. The test circuit is depicted in the left bottom is the pump skid with on the left the pump, in the middle of the hydraulic coupling, and the electric motor. 2 circuits are depicted, the blue one and the red one. The blue one is the heat exchanger circuit, where is an open circuit where the vertical pump take water from the pits and send ambient temperature water to the heat exchanger. After the heat exchanger, the water is sent to the test center evaporating towers. The red circuit is the main circuit for the boiler feeder water pump. Starting from the heat exchanger, the cooled water goes into the main circuit and goes in the suction pipe towards the suction flange, passing through the suction filter. From the pump, 2 circuits start. The smaller one, which is the bleed off circuits, and the big one, which is the delivery circuits. Both of them has the regulating valve, the flow regulating valve, in order to to regulate the correct flow and check the correct operating point. After the valve, both circuit has a magnetic flow meter to check the flow. After the flow meter, both circuits are directed towards the heat exchanger, where only a small quantity of water go in the heat exchanger. After that, both temperatures are recorded, and the circuit starts again towards the suction flange. So we have given a short introduction to the test. My colleagues will give you more detail. So I hand it over to my colleague Andrea Nicora, which will introduce also the question and answer parts. Thank you very much.
Okay, thanks to Fabio. The first part of our presentation is completed. Now, in a few seconds, we will connect to the test center. I see my colleagues already. Before that, just a request. After the test, we will have a Q&A, question and answer session, about 10 minutes. So please, if you have any request, any inquiry or any question, you can put them in the field. There is in the webinar page, you will find on the right a field called questions. You can digit your questions, and so we will collect them and prepare our reply, which will be given after the test. So thank you for now, and I leave the connection to my colleagues.
Okay, good morning, everybody. My name is Massimiliano Borghetti, and I am connected from Termomeccanica Test Center. First of all, thank you for joining our event. Here with me in the control room, there is Davide Rosato, that is the test center manager for Termomeccanica, and very close to the machine at the ground floor, we have Jacopo Manicardi and Marco Bianchi. Okay, a few words regarding the test, and mainly regarding what you are going to see this morning. The group is in the string test configuration. That means that we have the centrifugal pumps, but also all the other equipment in the design configuration. In this case, we have a train that is composed by centrifugal pumps that has been discussed by my colleagues, and an electric motor that is a huge electric motor of overall power by 6.3 megawatt, and in the middle we have an hydraulic coupling. As you know, the string test is very important for us, because it gives us the chance to test the group in the final condition, and so this is important for us to double check if the design is correct, but this is a nice chance also for our customer to test the group in the condition that they will have in the plant. Generally, the string test is a long test, because let's say we need to check one by one all the design points that are included in the test specification. Today we are going to show to you the potentiality of this group. So we are going to moving from low speed, that is 2000 RPM, up to the maximum P speed that is around 2800 RPM. And for each rotational speed, we are going to show to you how the point has been recorded and put in the final sheet. Okay, now Davide can explain to you how the group has been composed and which are the instrumentation that we have on board.
Good morning, nice to meet you. Now let's check more closely the installation to check together the instrument. Okay, on the video you can see the three lines where where the water flow. On the left we can see the discharge line with the four taps pressure for the discharge pressure. The second line in the middle is the bleed off flow, is the bleed off line with another 4-tap installation for bleed off pressure. And the first on the right, there is the suction line with another 4-tap pressure. Sorry. Okay, now we can continue moving the camera and to check together the other component. Ok, yeah, puoi muovere la telecamera. There is also 4-tap pressure for the first stage pressure in order to perform the NPSH test. Okay, on the video now we can see the variable speed coupling with flexible coupling covered by a protection. Under the protection there is the tachometer to measure the RPM. And on the right, we can see the electric motor. Ok, vai sui traduttori. Now on the video, you can see the instruments for to measure the pressures. Our pressure transducer in 420 milliampere. Ok, andiamo dall'altra parte. The pressure transducer are have a variable range of operation. Guarda un attimo le due valvole. Okay, now on the video you can see the details of the two valves to regulate the capacity. On the left we have the main valves for the discharge line, on the right the bleed off valve. Ok, inquadra le linee. To control the flow, we can operate the valve using a manual control directly on test bench. After the valve, the water goes in the discharge line where are installed the two flow meter to measure the capacity. There is a flow meter for the discharge line and one flow meter for a bleed off line. Okay, on the complete unit, we have also all the temperature sensor in order to monitor the temperatures. There is a temperature sensor on dry vent bearing, journal dry vent bearing, journal non-dry vent bearing, thrust bearing on the pump, then 3 journal bearing on the speed variable coupling, and two sensor on journal bearing for the electric motor. then all the temperature of a lubricant system. Okay, now we can see how all these instruments goes to the data acquisition that then that I show you on the video.
Okay, regarding okay, on one side we have all the instrumentation that has been properly described by Davide, and so from the control room we have the tool, the data acquisition system that help us to drive the test directly from the control room. Basically, we have some measurements that are directly done from the instrument, and those measurements are rotational speed, the actual rotational speed that you can see on the top left. So we have the direct reading of the absorbed power by the whole train. So we have the flow rate at the discharge flange. We have the flow rate at the bleed off flange. Okay, you know this machine is composed by 10 stages, but at the end of the third one we have a bleed off line, and so we measure with a flow meter the flow rate. And so we have all the pressure. We have suction pressure, discharge pressure. We have the measurement of the bleed off pressure, and also the pressure at the end of the first stage. This measurement is very, very important in the calculation, in the definition of the MPSH 3%. So on top to that, we have the reading of the vibration and the noise. Okay, so from these quantity are directly measured, but in order to properly record this value, we are used, based on our experience, not to collect the direct measurement, because let's say there is a difficulty to read the actual value, because there is small fluctuation. And so this acquisition system has embedded the capability to calculate the average. Okay, in this case, for this kind of machine, we generally use the average of the value between 20 seconds and 30 seconds. Okay, in this case, we are setting up the parameter for 30 seconds. So after 30 seconds, let's say the system is able to dispatch the value that we can put in the worksheet. The worksheet is used to recalculate all the other quantities that are necessary for the performance test, and there are very, very important quantities. For example, we have the hydraulic power for the machine, we have the hydraulic power for the bleed off. The sum of that is the hydraulic power of the machine. So if let's say we make the ratio between the hydraulic power and the overall power that is read by the instrument, let's say this ratio is the efficiency of the machine itself. So this is a very, very important measurement. So let's say this test has been done, let's say, regulating the water temperature with the system that has been previously presented by my colleague at the design water temperature that is equal to 157 degrees C. Okay, so let's say we can in 5-10 minutes show to you how this procedure can be applied, how the system works. So Davide is going to make 3 points, 2 at full speed and 1 point at low speed. This is just to figure out how this system works. Okay, David.
Okay, let's check the first point of operation. We are at 2,800 of RPM. The water temperature is stable. I start the first average. After the first point of performance, we can check directly on the pump the vibration and the noise level. Okay, you can see that the software gives us on the second line different measurements, and the numbers are stable, so I can stop the average and I can write the data on the calculation sheet. Okay, immediately the calculation sheet gives us the results, the performance of the of the pump at the design condition. You know, total head, shaft power, efficiency, and others. Okay, now let's check together the vibration values and the noise with the help of my colleague directly on the pump. Ok, procedi con vibrazioni e rumori. Using a portable vibrometer and a phonometer, the operator can check the levels. The measurement of vibration give us a RMS value. It is a root mean square value. Is in velocity, so millimeter on second. The measurement of sound provides that we have 8 points of measurement at 1 meter far from skid. The vibration checking also can do can give us the FFT spectra. The direction of measurement are directly on bearing housing, and the direction are vertical, horizontal, and axially. Okay. The measurements are finished, and this action is repeated for every performance point. Now we change the capacity, regulating the valves, and we repeat the data acquisition. Ok, andiamo a 580. Now my colleagues operating the discharge valve literally change the flow. For this test, we go to 480 of capacity. About. Okay, you can see that the flow is increased. Dacci un giro di velocità. Also, the speed is changed, so we can regulate the speed with the, the command for speed variable coupling. Okay, I think that this point is okay, so we can start with the performance. Sorry, with the average. Okay. The software is processing the data. And now you can see how the values change. When I see that the values are stable, I can stop the average. Okay, now I think that is okay, so I can stop and write the values on the calculation sheet. For this point is okay, so now we can change the speed and we go to minimum rotational speed, that is 2000, and we repeat the measurement. Ok, andiamo a 2000. Cioè. Operating the control of the speed variable coupling, you can see that the change of speed is instantaneously. Okay, let's take together the last point of performance. Bene, bene così.
Okay, basically, let's say we showed to you how the acquisition system works at full speed. So this machine has the nice feature to modulate the speed from minimum to maximum. And so basically the data acquisition system, the data procedure has been let's say, replicated in the same way. So I think that from the test center, let's say we can close and we can switch to the question and answer session. And if there are some questions regarding the test, we are here to answer. So thank you, everybody.
Thank you, goodbye.
Welcome back to our meeting room. We hope you enjoyed the test. By the way, Thermomeccanica Test Center is one of the biggest in Europe for a number of test loops and maximum capacity installed power, which is equal to 15 megawatts for the 50 hertz feeding and 5 megawatts for the 60 hertz feeding. So let's say is a strength of Thermomeccanica. We received just one question from during these minutes. The question is about the flushing system of the API Plan 23, which is the flushing system of the mechanical seal. And the question was about which measurement instruments are on the flushing system. Of course, you know that the API standards, let's say, establish which type of instruments shall be installed on the Plan 23. In our case, we have installed a free RTD, so temperature detection system with a logic 203 to check the temperature of the fluid entering in the mechanical seal. I hope to have replied to this question. Of course, we will send the presentation to all of you. And if you have any other queries or any other inquiry, you can send an email to our address, pumps@thermomeccanica.com. You can, sorry, there is another question just arrived. Are you sure the discharge pressure of 5 megawatt drive power was really 22? Otherwise, let's say the discharge pressure of the pump is yes, is 220 bar. This is the discharge pressure. Yes, we confirm.
Not a mistake.
No, yes, we confirm that this value is the right value. Sorry, we have just received this question. I was explaining that any other request or inquiry, you can send an email to our address, pumps@thermomeccanica.com, and we will reply promptly. We thank you very much for your participation. We hope to have given some highlights about this product and this project. So we thank you very much for being with us till the end of the presentation. I thank you also all my colleagues who have collaborated in this in the organization of this event, and all the project team who has developed this new product of Thermomeccanica. Thank you, and we wish to meet you in person at the next occasion. Thank you, and to the next time.